Hello and welcome back to another lesson in AP Stat class. Up to this point, we have learned four types of inference methods. The first one was a one proportion z interval, and then the second one was a one sample t interval. Both of those were confidence intervals. Then we learned about a one proportion z test and a one sample t test for estimating proportions and estimating means. Today's lesson is going to be our fifth method of inference test. It's called a matched pair t-test. Now, comparative studies are more convincing than single sample investigations. Therefore, a one sample inference is less common than a comparative study. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals results in paired data. Remember we did experimenting in chapter 4, and we talked about how we have different types of ways to design an experiment, and one of them was a matched pairs design. Right? We had a blocking design and a matched pair design. A matched pair design experiment results in paired data, and then results in what's called paired t procedures, or ultimately a matched pairs t-test. So when paired data result from measuring the same quantitative variable twice, as in job satisfactory, where we can measure, we can measure the satisfactory by doing one thing and then doing something else in the actual workforce, and then seeing if their job satisfactory is better or worse. We're comparing a pair. If the conditions for inference are met, we can use one sample t procedures, just like we did in the last section, but we're looking at the mean difference, which is the difference between the pairs, and then the average of the difference. Okay, you might call it a paired t procedure. You might call it a paired t test, a matched paired t test. All of them are considered the same thing. So we're going to look at an example. A researcher designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent or addicted to caffeine. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. Now, what they did was during one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took a placebo capsule. The order in which the subjects took the caffeine and the placebo were randomized. So the order in which they were given the pills were randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know if being deprived of caffeine would lead to an increase in depression. So we're going to analyze the data. First, I need you to input this data into list 1, list 2. I don't need all four lists. I need the depression in list 1 and then the depression of the placebo in list 2. So again, the depression of the caffeine in list 1, depression of the placebo in list 2. So pause the video and do that now. This data is the data of the subject scores on a depression test. A higher score shows more symptoms of depression. Okay, so like a score over 24 is very high for depression symptoms, while a score of 1 is very low of depression symptoms. You'll see the last list here, last row, is the difference between the placebo and the caffeine. We're not going to write this list down. I'm going to show you how to calculate it on your calculator. Okay, all we need is the 2 list. This list here is looking at the difference, a positive value, because we're doing placebo minus caffeine. A positive value means that the placebo had a higher depression score. A negative value, like you see way down here, shows that the caffeine actually had a higher depression score. Okay, this is the data we're actually analyzing, the difference between the placebo minus the caffeine. Now, when you're doing these paired t-tests, you could do placebo minus caffeine, or you could do caffeine minus placebo. You would get the same values, just the signs would change. And the only thing that would change on your actual inference test is your alternative hypothesis. Okay, so I'm going to do this whole test doing placebo minus caffeine. But if you did caffeine minus placebo, these values would be negative and then you'd be looking at just the other tail of the hypothesis test. It would give you the same result though. Okay, but it is important to tell me which one you're subtracting from the other, because the order does matter for your alternative hypothesis. First question is, why did we randomly assign the order in which the subjects received the placebo and the caffeine? Well, it's important to randomize in experiments. In this case, it's really important because the order in which the treatment that you receive could affect the outcomes. For example, suppose that the caffeine was all given to the subjects during the first 2-day period. What if the weather was nicer on this 2-day period? And the second 2-day period, when they were all given the placebo, the weather was terrible, right? A sunny day out affects your depression just like caffeine may affect your depression. So if we gave every subject the same treatment in the same order, and there was some outside variable also affecting these people, we couldn't tell if the weather or if the caffeine was the reason why they were becoming depressed. So therefore, it's very important to randomize the order in which you do this experiment. Okay, random assignment of the caffeine and placebo to the 2 time periods in the experiment should help ensure that no other variable is systematically affecting the subject's response. All right, so we're going to carry out a test to investigate the researcher's question. And our question is caffeine, does lack of caffeine cause depression? So again, we have our 4-step process: state, plan, do, conclude. Our statement: if caffeine deprivation has no effect on depression, then we would expect the actual mean difference to be 0. Right? If there was no difference between whether they had caffeine or they didn't have caffeine, then that means the depression scores should be about the same, and therefore when you subtract them, you get 0. Therefore, our null hypothesis is going to be that there is no difference, that mu sub d equals 0. We're going to use a lot of subscripts here. So sub d means the mean of the difference. The alternative is that the mean of the differences is greater than 0. Okay? And the reason why we're looking at greater than 0 is because we're doing placebo minus caffeine, which means a positive value shows that the lack of caffeine increases depression. Let's just say we did caffeine minus placebo. If we did that, we'd be looking at the other tail of the distribution, and therefore our alternative hypothesis would be mu sub d is less than 0 if we did caffeine minus placebo. So it's important for this sentence here to tell me which one you subtracted from. So mu sub d is the mean difference, not the difference of the means, the mean difference, placebo minus caffeine, in depression score for subjects like these. Okay? Again, we're doing an experiment, so we can only make conclusions about subjects like the volunteers in the experiment. Okay? We'll choose an alpha level of 0.05. That's our statement. Plan! Let's plan this. There we go. If the conditions are met, we're going to do what's called a paired t-test or a matched paired t-test. Either one's fine. You call it a paired t-test, matched paired t-test, it's all the same. Just know that this is not a one-sample t-test. Even though we're eventually going to do one-sample procedures, we are looking at a paired data. So random, because this is an experiment, we are not randomly sampling. We are randomly assigning the treatments. Okay, so the randomness here is random assignments, not random sample. We do not need to check the 10% condition here. We are not sampling. 10% condition is only checked if we are sampling. Okay, normal large counts. We don't know whether the actual distribution is normal, and the sample size is small, so we can't use central limit theorem. So we have to examine the data to see if it's safe to use T procedures. Now, how do we examine this data? Well, we could look at a histogram, we could look at a box and whisker plot, but obviously the best one, I think, is a normal probability plot. I'm going to show you all 3 here. Here's a histogram. Here's a box and whisker plot. Here's a normal probability plot. Okay, doesn't look super linear, but again, remember we're doing t procedures here, so our distribution doesn't have to be perfectly normal. It just has to be kind of normal, so we can use a t distribution as our estimation. Okay, but there's no outliers. It's not strong skewness, so we're okay with using a t procedure. Now, all of these distributions and graphs are made with the data that's the difference between placebo minus caffeine. We're not looking at list 1 and list 2. We're looking at what's ultimately going to be list 3. So I'll show you. In my calculator, I have list 1 and list 2. Here is the caffeine, and here is the placebo. What I want is list 3, which is the difference between these two. So I'm going to highlight list 3, highlight it. I'm going to do L2 minus L1. I'm going to hit enter, and it's going to give me all the differences. Okay, this L3 is the actual data we're looking at. So when we're making all of our graphs, so I'm going to turn on my stat plot, and let's make a normal probability plot together. Here is my normal probability plot. It's not going to be list 1. It's actually going to be list 3, because that is the data I care about. When I hit graph, I gotta hit zoom stat. There it is. That's what you see on the PowerPoint as well. We're looking at just the data in list 3, which is the difference between the placebo and the actual caffeine. Okay. Now, when we're doing this in our do section, again, we're only using the data that's the difference, so it's going to end up being the same test in our calculator. So if I go to my calculator, I have my data in list 3, because list 3 is my important data, which is the difference. If I go to stat, I'm going to go over to test. It's still going to be called a t-test in my calculator. It's not a one sample t-test, but because we are looking at the difference between paired data, it ends up being the same process as a one sample t-test. Even though it's called a matched pairs t-test, we're still looking at one sample. It's just the difference between pairs. Okay, so I have data. My null hypothesis is 0. My data is actually in list 3, so I'm going to highlight list 3. And I'm looking for greater than my null hypothesis. And then I hit calculate. Boom. And you'll see I get a test statistic, or a t-score, of 3.53, which is very big, and a p-value of 0.0027, which is very small. Okay? And my degrees of freedom here, because I have a sample size of 11, my degrees of freedom is 10. So this is how I would get my p-value and my test statistic. Your book loves using doing things by hand. You definitely don't have to do it by hand. You're going to utilize the use of a calculator. So your test statistic and your p-value here. And your conclusion, you're going to compare your p-value to alpha. So because my p-value is 0.0027, which is less than alpha, we're going to reject the null hypothesis. We have convincing evidence that the true mean difference in depression scores is positive for subjects like these. AKA, we have strong evidence that depriving people who are addicted to caffeine, actual caffeine, then leads to higher depression scores. That's what we're saying in this inference test. A match paired t-test. All right, some things we need to keep in mind when carrying out a significance test. A smaller significance level, so alpha, a smaller level of alpha requires stronger evidence to reject the null, which makes sense. If alpha is 0.05, we don't need as much evidence to reject it, whereas if alpha is 0.01, we need stronger evidence, aka a sample statistic further away from the actual parameter, or the proposed parameter. Higher power, right, the power of a test, gives a better chance of detecting a difference when it really exists. So remember, the power of a test is the probability of successfully rejecting the null hypothesis. And at any significance level and desired power, detecting a small difference between the null and the alternative parameter values requires a larger sample, right? If we go back to the very first example we did where I claimed that I was an 80% free throw shooter, let's just say that I wasn't an 80% free throw shooter. Let's say that I was actually a 78% free throw shooter. 78 is pretty close to 80. It's going to take a large sample for you to actually detect that I'm not an 80% free throw shooter. I'm actually something a little less than 80%. So if the difference between the actual parameter and the hypothesized parameter is small, it'll take a very large sample to detect that small difference. When a null hypothesis can be rejected at the usual levels, there is good evidence of a difference, but the difference may be small. When large samples are available, even tiny deviations from the null hypothesis will be significant. Right? When we reject a null hypothesis, we don't really know what the parameter is. We just have evidence that it's not the hypothesis that we claimed. We don't know how far away it is from the actual claimed hypothesis. Right? It could be close, it could be far. I could be a 78% free throw shooter, and you would reject my 80% claim. Or I could be a 60% free throw shooter, and you reject my 80% claim. Right? They're both a rejection. You just don't know how far away I am from my claimed parameter. So just be careful of that. Okay? And be aware of multiple analysis. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking, design a study to search for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. Okay, so this is just if we're looking at in the real world, just beware of multiple analysis. All right, here's an example we're going to work through. I'm just going to show you how we could do this. So go ahead and pause this video and read the question and input this into your list 1 and list 2. We'll do one more example together. And this is a problem that says, for the second semester project in AP Stat, Libby and Catherine decided to investigate which line was faster in the supermarket, the express lane or a regular lane. To collect their data, they randomly selected 15 times during a week, went to the same store, bought the same item. One of the students used the express lane while the other used the closest regular lane. To decide which lane of them they would use, they flipped a coin. They entered the lane at the same time, paid with the same method, recorded the time in seconds it took to complete the transaction, and here is their data. So you'll see the time in the regular lanes on the left, the time in the express lanes on the right. Okay? Carry out a significance test to see if there's convincing evidence that the express lane is actually faster on average. Okay? So, just remember that a larger number here means slower, right? Larger numbers mean slower because it means more time was taken. Okay, so we got to create hypotheses. Here, because I chose to do the regular lane minus the express, that means my null hypothesis is always going to be there's no difference between the pairs. My alternative hypothesis is that the mean difference is greater than 0 because I'm doing regular minus express. And what I'm saying is that mu sub d, which is the true mean difference in the time required to purchase an item at the supermarket, is actually bigger than 0, meaning that it takes more time in the regular line. I chose an alpha level of 0.05. And my plan section. Okay, if the conditions are met, we're going to perform a paired t-test or a matched paired t-test, whatever you like to call it. This was a random sample of times to make the purchases that were selected. We are going to assume that 15 is less than 10% of all possible visiting times in the store. Now you might be wondering, why are we checking the 10% rule here, but we didn't check it in the last problem? Remember, the last problem was an experiment with volunteers. This is not an experiment. This is a sample. I randomly sampled 15 times. And that's why anytime we are sampling, we have to check a 10% rule. And then normal, again, 15 is less than 30. So therefore, we need to actually graph, some sort of graph, and in this case I chose a normal probability plot, and you will see my normal probability plot below. Again, my normal probability plot is a plot with my list 3 data, not list 1 or list 2, right? I put time in regular lane in list 1. I put time in express lane in list 2. My list 3 is list 1 minus list 2, because I did regular lane minus express lane. If you flip these, if you did list 2 minus list 1, all that would do is it would change your alternative hypothesis. You would make mu sub d less than 0, and then you would just do express minus regular. But your conclusion will be the exact same. You'd be looking at the other tail of the distribution. Okay? In my new section, you need 2 things. You need your test statistic, which is 1.97. You have p-value, which is 0.035. And you actually need your degrees of freedom, which are missing here. And degrees of freedom are 14, because my samples are I have 15 paired samples. So degrees of freedom are 14. Don't forget the degrees of freedom. In your conclusion, you are going to do 3 things. You're going to compare p to alpha. Right? You're going to then either reject or fail to reject, and then put it in context. So the p-value is 0.035, which is less than alpha of 0.05. We're going to reject the null hypothesis because p is less than alpha. There is convincing evidence that the express lane is faster than the regular lane on average. Nope. That's it. Okay. We'll see you in class.